Hello, my name is Hubert Głowiński. I'm from Institute of Molecular Physics, Polish Academy of Sciences, from Poznań, from Poland. My today's topic is the correlation between orbital magnetic moments and effective magnetic anisotropy in gold, cobalt, iron, boron, gold systems. First, I will show you and I will tell you about our motivation to conduct those studies. And this motivation is in fact a relation between anisotropy and damping and other surface phenomena which occurs in thin film systems. And of course I will show you how looks the anisotropy of these cobalt iron boron films in vicinity of gold. And one of the most important parameters which governs a lot of phenomena in thin film magnets is spin orbit coupling. For example, this Bruno formula shows that magnetic anisotropy energy is proportional to the spin orbit coupling. Damping was shown that is proportional either to cubic or square of spin orbit coupling. Also, other like Głowiński-Moria interaction is also a function of spin orbit coupling. Mutual studying of those measurable parameters like Głowiński-Moria interaction, damping and perpendicular magnetic anisotropy could thus give some information, for example, about the spin orbit coupling of the spin orbit coupling parameter. And in fact, it was shown in this paper. This is one of the examples which can be found in the literature. What authors concluded from those measurements was that they measure in a function of PMA of anisotropy, and they measure damping, delta H0, and the ratio between orbital to spin moment. And what they found that damping is constant, and they concluded that means that also the spin orbit coupling is constant. They found that in homogeneous broadening, this delta H0 parameters is increased with increasing value of PMA, and also they correlate this ratio between orbital to spin moment and effective magnetization, which is a measure of anisotropy. So they concluded that the spin orbit coupling does not change in this system, and what they change, they modify the delta μL parameter according to this formula. The anisotropy in cobalt iron boron system was already the study of this were really boosted by this paper of Ikeda et al. When they find that after annealing they can achieve perpendicular magnetic anisotropy in system of tantalum cobalt iron boron MgO. And they showed, as it's seen at this picture, that below approximately 1.5 nanometer, they have perpendicular magnetic anisotropy with very low coercive fields. Vertical study are not really able to study amorphous films, so from that time a lot of papers were done on crystalline structure with cobalt ion, because it is believed that after the annealing, this amorphous cobalt iron boron film converts to crystalline structure, crystallized. And this is one example of this vertical paper which showed that this cobalt iron deposited onto gold substrate can achieve from some compositions perpendicular magnetic anisotropy, but it is the smallest anisotropy comparing to copper substrate or MgO substrate. Another vertical paper also showed the system MgO cobalt iron boron with some other materials, and they also studied only one interface here. And what they found it is that gold gives almost no magnetic anisotropy, and so the whole anisotropy of this MgO cobalt iron boron gold system is due to an interface with MgO But in literature it was found that this alloy iron with cobalt could exhibit perpendicular magnetic anisotropy, deposit onto gold and covered with MgO. But up to today there were not very much results without MgO array, so we don't know if this MgO array is crucial for achieving perpendicular anisotropy. A few years ago we found that amorphous without annealing cobalt iron boron film between two gold layers can exhibit perpendicular magnetic anisotropy, here seen as a rectangular hysteresis loop measured with TMAG. So easy direction is the out of plane direction, and we can see that for some range of thicknesses we observe non-zero coercive field, and we observe rectangular shape because remanence co-rotation is equal to saturation co-rotation. We also studied this film using ferromagnetic resonance, broadband ferromagnetic resonance, and we were able to measure G factor, damping, and also delta H0 parameter. And we found that both G factor and damping scales with inverse of cobalt iron boron thickness. What suggests us that there is some surface contribution to the G factor, and we also found that the surface contribution to the damping, which is known effect as a spin pumping contribution to the damping, which is described by effective spin mixing conductance. This is the value which we found. We also found in many papers also that with decreasing the thickness, increase the inhomogeneous broadening, so increase the inhomogeneity or magnetic inhomogeneity of our sample. We also studied crystalline films deposited onto gold and covered with different cap layers with gold, copper and nickel oxide. In all cases we observe for some range of thicknesses perpendicular magnetic anisotropy, which is shown here as a rectangular hysteresis loop. So we have two systems. One is amorphous cobalt iron boron and one is crystalline. In both cases we observe perpendicular magnetic anisotropy for different spin rotation transition thicknesses, mainly due to large, this thickness is lower mainly due to large saturation magnetization of this alloy, and we also measured, of course, the anisotropy parameters by means of TMAG and ferromagnetic resonance, and we found that, for example, in this case of crystalline cobalt iron, we have obtained a very big surface anisotropy. By measuring G factors, we are able to calculate the delta μL versus μS ratio. As we can measure, like here, the μL versus μS ratio is a function of G factor according to this formula. We measure it for both crystalline cobalt iron and for amorphous cobalt iron boron. Unfortunately, due to large saturation magnetization, we are not able to measure precisely this parameter for thick films because we have not enough field to saturate the sample. But we are able to measure the full range of thicknesses for cobalt iron boron film. So, going to cobalt iron boron, we can observe that the sign of delta μL versus μS film changes its sign in approximate the same position, but not exactly the same position, where the spin rotation transition occurs. Here we have a negative sign of this ratio, and here we have positive sign. So so maybe it is somehow connected to this formula where we observe the change of this delta μL parameter is the change of the sign of delta μ parameter is related to the change of the sign of the magnetic anisotropy energy. We also have some preliminary theoretical results on, of course, not amorphous but crystalline structures, and the first theoretical results are these iron slabs with vacuum on the other sides, and we also observe the change of magnetic anisotropy energy and similar changes of μL to μS parameter observed decreasing with decreasing thickness of in plane direction and increasing with decreasing thickness of perpendicular direction. To sum up my talk, we obtained the values of surface anisotropy parameters for two systems, for amorphous and crystalline one, and we obtained a very large value of this surface contribution for this crystalline one. And we found a correlation between delta μ and between a ratio of μL to μS moments and with anisotropy. Thank you for your attention.